Slope solutions in implicit functions still follow the same algorithm to figure out the derivative of the equation. Check how it works here in differential calculus. In slope solutions, there is only a single step added to the implicit differentiation procedure. The first steps are the same like differentiating all terms in the equation, collecting every term with y prime to one side, factoring out y prime, and then solving the equation by simplification. The additional step is to plug the coordinates of the point of concern to get the slope. The first illustrative problem involves the equation x squared plus y squared minus 12x plus 4y is equal to 5. And we are to look for the slope at point 0, 1. Start with placing the derivative with respect to x to all the terms. So we have the derivative of x squared as 2x times dx all over dx. The second term with the derivative of y squared is simplified as 2y dy all over dx. The third term is differentiated as negative 12 times dx all over dx. Then the derivative of 4y is 4 times dy all over dx. On the right side of the equation, we can differentiate 5 as 0. Next, by simplifying dx all over dx as 1 and dy all over dx as y prime, we simplify the equation into 2x plus 2y y prime minus 12 plus 4y prime is equal to 0. We continue by collecting terms with y prime and pushing the others to the opposite side, and then simplify further by dividing everything by 2, we get y prime plus 2y prime is equal to 6 minus x. Factor out y prime to arrive at y prime times the quantity of y plus 2 is equal to 6 minus x. So the derivative of the equation is y prime is equal to 6 minus x all upon y plus 2. At this point, we use the coordinates to find the slope. So we plug in x of 0 and y of 1 in the equation. To get y prime is 6 all over 3, or that is y prime is equal to 2. We work on the equation the square of x plus 2y is equal to x plus 10 at point negative 1, 2 for the second example. Place d all over dx in all terms to start the differentiation. On the left side, the derivative of the whole square is 2 times x plus 2y, then the derivatives of each term turn out as dx all over dx plus 2 with dy all over dx. On the right side, the first term becomes dx all over dx, hooked with 0 as the derivative of the constant 10. Simplify dx all over dx as 1 and dy all over dx as y prime to have 2 times the quantity of x plus 2y multiplied by another quantity 1 plus 2y prime is equal to 1. We move to the next step of collecting all terms with y prime to the left corner of the equation. Y prime is grouped in the quantity 1 minus 2y prime, so place all over groups of terms to the right side. Next is to isolate 2y prime by transposing 1 to the rest of the equation on the right. Work with the equivalent fraction to convert 1 into a fraction, with LCD to reduce the equation into 2y prime is equal to 1 minus 2x minus 4y all over twice of x plus 2y. Finally, move 2 to the other end again to have y prime is equal to 1 minus 2x less 4y all upon 4 times the quantity of x plus 2y. Plug -1 as x and 2 as y to get the slope of the curve as -5 all over 12. Let's have an example with variables as coordinates. The equation involved is y squared is equal to b cubed all over 2x plus b with the point 0 and b. Insert d all over dx to all terms. But before continuing, take note that b is considered a constant, as the only variables in the problem are x and y. So having b as a constant, we can avoid using quotient rule by placing the constant out and working on the reciprocal of the denominator. So the function turns out as d all over dx of y squared is equal to b cubed multiplied by d all over dx of the quantity 2x plus b, this time raised to -1. Now we are ready to differentiate. The derivative of the left side term is 2y times dy all over dx. The right side of the equation is derived as b cubed multiplied by -1 of the group 2x plus b, which is then raised to -2. Continue with the derivative of the first term, which is 2 dx all over dx, plus the second term db all over dx. Convert dy all over dx as y prime, and dx all over dx as 1. Also, the derivative of the constant b all over dx is 0. To simplify the equation, we have 2y y prime is equal to -2b cubed all upon the square of 2x plus b. Place 2y down to isolate y prime and have y prime is equal to -b cubed all over y multiplied by the square of 2x plus b. With the coordinates 0 and b plugged in as x and y, we get -b cubed upon 0 plus b cubed, which is then reduced into y prime as -1. Example 4 has the equation y squared is equal to 2a cubed x all upon x squared plus a squared, where the point considered is at a. Again, insert d all over dx to each term. The left term is simple, but the right term is longer. For this problem, 2a cubed is considered a constant, so we can extract it out before the derivative. Next is to differentiate. So the left term becomes 2y multiplied by dy all over dx, and the right term has 2a cubed and the derivative of a quotient, which can be continued as taking low d high minus high d low all over the square of the denominator. Let's simplify the equation a step at a time. So we simplify dy all over dx into y prime and dx all over dx as 1 to get 2y prime is equal to 2a cubed all upon the square of x squared plus a squared multiplied with the quantity x squared plus a squared minus x times 2x dx all over dx plus 0. And again, we simplify dx all over dx to shorten the equation into 2y prime is equal to 2a cubed multiplied by the quantity of x squared plus a squared minus 2x squared all upon the square of x squared plus a squared. We take y prime by moving 2y to the other side of the equation to get 2a cubed multiplied by a squared minus x squared all upon 2y multiplied by the square of x squared plus a squared. Then we cancel out the 2's to arrive at a cubed multiplied by a squared minus x squared all upon y times the square of x squared plus a squared. At point AA, y prime can be taken with x equal to a and y equal to a, making y prime as equal to a cubed times 0 all over a times the square of 2a squared, which can be reduced further as 0. For the fifth example, we are to look for the slope at point 42 on the curve described in the equation y multiplied by 3x minus y squared is equal to 16. Plug d with respect to dx for all terms. And note that we need to employ product rule on the left side of the equation, and that is using the first term y times the derivative of the second term 3x minus y squared plus the second term 3x minus y squared times the derivative of y with respect to x. This whole expression is equated to the derivative of 16, and that is 0. dy all over dx is taken as y prime to simplify the second term. Focusing on the first term, we have y multiplied by the derivative of 3x, which is 3 times dx all over dx, minus the derivative of y squared. Take dx all over dx as 1, then continue with the next derivative, which turns out as 2y times dy all over dx. So after eliminating these, the equation becomes 3y minus 2y squared y prime plus the quantity of 3x minus y squared multiplied by y prime is equal to 0. Isolate terms with y prime, and the term 3y is moved to the other side. Factor out y prime from the two terms, and then have those terms moved to the other side of the equation to get y prime is equal to 3y all over 3y squared minus 3x, where we can cancel out 3 to have y prime is equal to y all upon y squared minus x. At point with coordinates 4, 2, we have y prime is equal to 2 all over 2 squared minus 4, which is reduced to 2 all over 0, making it undefined, and this means that the slope at that point does not exist.